All right. So today I want to talk a little bit about positional analyses. And this is the distinction, if you remember. I think I actually probably still have the slide. Yeah, here we go. This distinction that we make in our book, and that we've been trying to sort of get people to sort of frame their thinking about networks around, is that networks aren't just one big thing. There's lots of different ways to use networks. And the way we've traditionally used networks is this networks as pipes model. But there's this whole sort of literature that sort of, in many ways, sort of sucked a lot of us sociologists into networks in the first place. That we want to think about networks as systems of relations, and that people occupy different positions in the systems of relations. And that there's oftentimes at the social level a logic to the organization of these positions, and that the social system itself is organized in a particular way, and the traces of that come out as roles and role systems. And so these ideas of a role and role system fit deeply with the notion of networks, and this is part of the reason that many sociologists got interested in it, besides the fact that it has the diffusion side. The diffusion side, I'm just going to tell you straight up, is, like I said the first day, the diffusion side is, the connectionist side is more well developed. The tools there have, because of their obvious use in disease diffusion and other kinds of peer influence and so forth, there's just been a lot of money and interest put in it, whereas the positional models have been developed largely by poor anthropologists on a shoestring without a whole lot of money behind them, and so you haven't had a lot of the same kind of interest. I think that's too bad in many ways, because as I hope to convey to you anyway, I think that these kinds of models can be really powerful and really tell us something about the world that we don't otherwise get. The archetypical example of a positional model is kinship systems, which is why I've put Ashton and I next to each other. And so this will be the general case, and then Ashton will take you on to the specific case. But the way we want to think about positional models is a little bit of sort of this idea of a coherence of roles. So social life can be described through these social roles, and to the extent the roles can be characterized by regular interaction patterns, then we can summarize roles through these common relational patterns. And what I mean by that is that almost any time you imagine your interactions with somebody else, you can characterize them. If that other person has a title, you can characterize your relation with them by a specific type of thing you exchange. So the classic example I always give is that teachers exchange assignments with students, and parents exchange discipline with kids, and lovers exchange affection with each other, right? And so there's this effect of which, when we have an ID, some kind of a characteristic, that there's an exchange process that goes with it. And anything that you can exchange with someone, you typically exchange because you're complementary, right? So there's this classic line from Adam Smith that no one's ever seen a dog exchange a bone for a bone, right? That's because dogs are substitutable. It doesn't make any sense. I already have my bone. I don't need your bone, right? But if I'm selling cars, right, I need buyers that give me cash. And so there's a sense in which there's a complementarity that comes through social exchange, and that's the foundation of role systems. That when you live in a large, differentiated society, we don't all do everything the same all the time. We do different activities with respect to each other, and we have a division of labor, and that division of labor creates a necessary exchange. And that's obvious in the economic world. That's the world that we're, especially in the West, that we're so used to thinking. But it turns out, and this is why the structural anthropology is so beautiful, it's true in the symbolic world as well. So we exchange meanings, and there are types of people who are experts in producing meanings, and other people who come to them in order to consume those meanings. We call them shamans and priests and so forth. And so their job is to help shape meaning for us so that we can interpret the world around us that is otherwise a mess. And so there's this exchange process that's engaged in all of social systems, and we understand each other by virtue of the fact that what you do fits into a box based on your role and my role. Now, what was really interesting about this idea, now this idea is an old idea, and so Nadel's The Coherence of Role Systems posits that the fact that we can get along in society is that we implicitly learn these. Part of what it means to grow up in a society is that we understand the implicit meanings of social exchange systems in a way that allows us to be competent navigators of the social landscape. So we can move around and it makes sense. And anybody, as part of the brilliance of travel, the reason it's so fun to go to another country, particularly a country where you don't read the language, is that you've othered yourself and you get to experience that immediately. So as soon as you step off the sidewalk and realize that the rules here are a little bit different, that's that example, that You're no longer fitting into the system that's set up there. The role system idea that comes out of, like I said, about structural anthropology. The brilliance of White, Borman, and Breiger, the original social structure for multiple networks papers, is that they flipped this around. And they said what traditional role theory has done is said, you give me a set of roles, I will enumerate from that the set of exchange patterns. But there's no reason you need to go from roles to exchange. You can flip it around and go from exchanges to roles. And that's brilliant, because what it allows you to do is to uncover a set of roles that don't otherwise have names. And so there are a whole series of regularized interaction patterns that we engage in that don't have names, right? Informal leaders and brokers and other kinds of things in families, the person who you always put next to your drunk uncle at Thanksgiving to sort of keep them in check, right? That person doesn't have a role. They probably have a name in your family, but I think everybody in every family has one of those characters that fills that position, right? They're sort of the referee of some sort, right? And so these notions of have a role is what we would like as sociologists and anthropologists to be able to have a tool set that lets us identify them, because clearly they matter. They're engaging in the way that people, they're activating the way that people engage the world. And so if we can find them, right, that makes it possible for us to study them and explain them and do all the things that sociologists do. And so what White, Borman, and Breiger did is they took the logic of kinship models and this notion of compounding relations and used that to describe all kinds of social relations. And so what I mean by the logic of kinship relations, I don't know if I brought this slide with me, is that there's a certain set of roles that fit together in a way. And some of them are these necessary roles, right? And so if you could imagine that, the kinship example just comes to mind because it's easy, that my mother's brother's son, right, is my male cousin. My mother's brother's daughter is a female cousin. My mother's brother's son is probably me, right? And so you can imagine thinking about the way these orders of relations go. And my father's 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 father is my great-great-great-grandfather, and so forth. And so we have these compound relations. Well, you can compound other kinds of relations. So it doesn't just have to be biology and descent, like my husband and my children. It could be, the relation could be informal. It could be a friend of a friend. So a friend of a friend also has a conjunction. We call a friend of a friend an acquaintance, if not a friend. My enemy's enemy is probably an ally, right? My lover's lover better be me, right? So that's the kind of model that we think about, right? And so this notion of compounding relations has a chance to sort of fill out to the kind of things we expect to come out of those systems. And just like we expect ants to behave in certain ways, we expect our lover's lover to behave in certain ways, right? So this is the way that this is the kind of idea that they have. Now, the biology versions, the kinship versions, are necessary. They're built into the grammar of the relationship themselves, or in the biology of the relationship, or the formal law of the system, right? The one thing that most sociologists care about are these coincidental roles. These are roles that pop up out of the feature, not because they have to, but because of either some creative social action on the part of the actors, or capitalizing on a random sort of series of events that made a position particularly meaningful, that then gets reinforced and renamed. So this is the example that I gave on the first day, right? If I have 5 actors, and I describe their social relations, we have romantic exchange, we have feeding, and we have bickering. This is the classic, comic family. And the fact that part of the reason I use this example is that it has a set of characteristics that I think are nice about sort of a general illustration of roles in social networks. The first is that it's a combination of different types of relations. So you can do block modeling, you can do relational analysis on single relations, and I'll show you an example of that. Excuse me. But it really shines when there are these different kinds of relations, right? Because that's where you get the opportunity to see the intersections of sort of the spread of an exchange process across a single dyad. So a single dyad will exchange one thing. So lovers exchange one thing, right? But lovers and their kids exchange necessarily something different. But the romantic relation sort of investment gets invested through the feeding of the kids into the parents' investment of the kids. And so this kind of joint sharing carries some meaning through it by the fact that these relations have a conjunctive nature to them, which I think is nice. The other thing, just from a practical standpoint, is you'll notice is that we have some symmetric relations, some asymmetric relations. Feeding, in this case, is actually anti-symmetric. Kids don't provide for parents, parents provide for children, and so you have this kind of mix of different kinds of relations. Lots of different kinds of these relationships. I've kind of already said that, so I won't say it again. I think that we want to think about this. One bit I would point out is that it's easy for us in the West, in particular, to think of these labels as attributes of nodes. What Nadell wanted us to think about, and what the classic work in structural anthropology wanted us to think about, is that roles are actually a collective property of the social system. So aunts have a meaning, right? And so if you've ever got hooked on Indian matchmaking, like auntie is a word, right? And auntie means something in the Indian context that is not just my mother's brother, right? Or my parents' mother, sister, excuse me, I'm getting you through it, right? And so this idea that we have a collective understanding of these roles should be true not just for formal roles like deans, but also for informal roles like broker or fixer, right? And those kinds of things. Yeah, I'm going to skip that part. All right, so there are, in general, in network analysis, so that's the sort of the big theory, and I would love to sit down over a little bourbon with you at the end of the day, and we can think about this sort of wax philosophically. But my pedagogical moment now is to move to sort of like, what do we do with this? Like, how do we actually do this kind of analysis? And there are two ways that traditionally that sociologists have done this. One has been a sort of a micro way, and the other is a collective way. The micro way is through centrality analysis. And there's a whole bunch of work on centrality. I talked about that briefly in the set. Centrality has, again, sadly been co-opted largely by the connectionist folks, particularly thinking about the ways in which centralities are thought of as path compoundings. And so you can either be a radial or central or medial and so forth. But in the interest of time, I'm not going to talk about the centrality version of positional analysis today, other than to say you can do a lot of positional analysis using centrality scores in a way that is really easy to do. You just don't think about them as by virtue of their property of having collected something and passed it through. You think of it as something that uniquely identifies a place in the network that a person lives. So if you just shift your interpretation of why it matters, you can do it with centrality scores as well. But I want to talk about the collective version of this right now. So the collective version, the idea here is that, so I'm going to skip over the centrality. The collective version is that we have some set of relations, and so now what we want to do is identify a partition on these relations, a coloring of the nodes that says that this set of nodes differs from this set of nodes. And so the way we do this is called block modeling, and I've deliberately in the title of this slide referred to as relational block modeling, because in the statistics world now, this has been co-opted to mean stochastic block modeling, which is just a different word for community detection. And stochastic block modeling is a type of community detection. Relational block modeling is finding roles in networks. So first you have to identify a notion of equivalence, and this is something that makes two actors the same in the network. Once you have that, you need to measure the degree to which pairs are equivalent, develop a representation of that equivalence, and then assess the adequacy of the fit. So these last two are largely what you would do for any kind of descriptive analysis. These first two are what part that makes it unique for social network analysis. In general, the broad class of equivalence that we're dealing with is this thing called structural equivalence. So structural equivalence says that two people are the same in the network by virtue of their pattern of ties. Now, there's a whole lexicon of special terms: structural equivalence, regular equivalence, automorphic equivalence, isomorphic equivalence. I'm not going to go into detail on what each of those are, because frankly, at the end of the day, it rarely matters, right? There's specific algorithms for one over the other, but I want you to get the intuition for why this matters, and then I'll point out the different cases you can use. So a structurally equivalent node, right, two structurally equivalent nodes should be indistinguishable in the network. They have the same pattern of ties to the same set of alters in the network. Now, perfect structural equivalence means they're truly substitutable, that if I'm tied to Craig, then my structural equivalent is also tied to Craig. If you've ever taken a new boyfriend or girlfriend back to your hometown and had them mistaken by your friends for your ex-boyfriend or girlfriend, you know what structural equivalence means, right? That kind of awkward moment, that's structural equivalence. And you don't want that, right? That's a case where it induces a set of problems. But from a standpoint, from our standpoint, from a methodological standpoint, you want to find a way to take these separate relations and figure out how a pair of nodes is the same across all of these relations. And the intuitive, simple way to do this is to stack the relationships. So you take your romance network, you put it up here, you take your feeding network, you put the direct network there, and the transpose there, and the bickering network there. Right? And you can do this for as many relations as you want. Now you might ask yourself, why did I transpose and double count the feeding network? It's because I want to distinguish not just that I feed Craig, but Craig receives feed from me, right? So this notion that there is both a sent and received ties helps you figure out whether or not there's an internal reciprocity that is meaningful in this setting. And so usually, a lot of the routines in the R right now will automatically transpose all the relations. And so they actually double count these necessarily symmetric ones. I think practically you're better off if you just double count the ones that are asymmetric, because then you're not overly weighting those ties. But there's not a whole lot of simulation work on this to know how these matter. Then all you do, once you've stacked the relations, by virtue of this trick, now really the columns is where all the information is. You don't really care so much about the rows. And so what you want to do is say, is this column the same as this column the same as that column? And you can do that with whatever your favorite the same statistic is. Traditionally, it's been correlation. So we ask, how often does this column correlate with this column? And in this little toy example, and the reason we recognize it so well, is you have perfect correlations within position and zero correlations, probably actually negative if I actually calculate it. But we can see that these guys are actually the same. So they match on every one of these dyads. They're the same. And every one of the dyads, those three are the same. And that's your similarity score. Now there's a bunch of different similarity measures. In the R package that Carter Butts wrote that I'll show you today, there's the common ones are counting distances. So you have Hamming distances, you have Jacquard distances, and there's versions of the correlations. So you have the regular correlations or a regular equivalence version of correlations. Excuse me. Now I'm going to spend a little, so the structural equivalence is the version that we always hear people talking about as part of the White-Borman-Bragger paper. In that version, it's the same two people are tied to the same nodes. And to the extent that these operationalizations matter, one of the problems of that same set of ties to the same set of nodes does for us is it ends up conflating equivalent types of positions with clusters. And so structural equivalence will have a bias towards finding communities. And so the distinction between roles and communities gets a little bit blurry when you're dealing with structural equivalence because of this reliance on the same side of others. Automorphic and regular equivalence says that are a little more general. So what they're saying with automorphic equivalence, you have the same pattern of ties to all others of the networks. And so nodes are indistinguishable on any summary statistic. So keep that in mind. So what you're really saying is that if I were to have the number of ties, your betweenness centrality, the size of the number of people you can reach in 2 steps, your inverse score on the Laplacian matrix, right? You can find me any crazy score you could invent on a network. If the nodes are automorphically equivalent, then they should have the exact same score. Now, a slightly more generalized version of that is regular equivalence. In regular equivalence, we say that I have similar types of ties to similar types of others. If automorphic equivalence is co-word in a network, a regular equivalence is co-meaning in a network. And so this is what old style co-word analysis would do. This is what GPT would do, right? And so I can say, the cat got chased by the dog, and the squirrel got chased by the coyote. Those two things have no words in common, but they mean effectively the same thing, right? And so regular equivalence is an attempt to try to figure that process out. Again, a lot of times these distinctions don't make a whole lot of difference, except that when you try to look up the algorithms for them in the literature, you're going to find slightly different algorithms for all 3 of these. This tends to be done with concore in correlations. This is done with clustering on observed statistics, and this is done with a specialized algorithm called REGE, R-E-G-E. which is regular equivalence generation something. I forget what the last E stands for. To give you an intuitive sense of what this looks like, as a viewer, you can look at this and you can probably tell me which of these nodes are the same, right? So you can say, well, look, there's somebody at the top of a hierarchy, some vice presidents, and some graduate students, right? And so you have this kind of model sort of fitting in the world. And if you run Concore on this, what you can do is you can say, to do that, what you would do is you would take this adjacency matrix that we've observed in the network. It's a symmetric matrix, so I don't have to worry about flipping it in any way. And I would just take each column and I'd correlate it with every other column and generate a square correlation matrix. Now, your perfectly structurally equivalent nodes are going to have a correlation of 1. All right, and so this is the intuition behind why you would use correlation to capture structural equivalence. But the beauty of the Concore algorithm is that if you now say, well, there's some information embedded in this, and I know that this position is, this person is structurally equivalent to this person, but what I'd like to know is how similar are these two to each other, and I don't know how to interpret a minus 0.2 correlation. I don't know what that means. But what Breiger, Borman, and Wright figured out is that if you take this correlation matrix and correlate it with itself, and you do that again and again and again, the thing breaks up into these two beautiful parts, right? One block of all ones and another block of all minus ones. And my lines got messed up here at some point, but the line's actually right there. And so, and this is a feature of correlation matrices. The power sequence of correlation matrices will always converge onto two sets, one with all positive sets and one with all negative sets. And that then becomes the basis of your divisive algorithm, to use a language we used last time. And so for any given network we see, we can run that little process, we can split it into two, and we get a split between us's and them's. And then within the us's, we can split them between the, the holy and the heterodox. And we can just keep doing this splitting on and on and on as we go. This notion of the way that Concore works is both a feature and a bug. By virtue of a binary split, each time you do this, sort of if you just apply this in a rote way, you're either going to get 2, 4, or 8 clusters if you go for 1, 2, or 3 splits. Of course, you don't have to do that. The smart thing to do is to split it at 2, evaluate it. If it looks like it needs to be split again, split each branch separately, and then you can get as many splits as you want. And that's intuitively what we do in our software. Give you an example of how this works. This is the co-voting network in the Senate. And so here you see that each person is tied if they voted the same on a bill. And you can go ahead and sort of sort those into people who are exactly the same number of ties they voted together. That's what we have there. And then we can run that through Concore. And when you run it through Concore, what you find is that these are sets of nodes that are all structurally equivalent. And so you have, this is 2 different versions of the Senate, but in this case, in the 103rd Senate, we have 2 largely fall in line kind of Democratic clusters, 2 largely fall in line Republican positions, and then a set of smaller positions where people aren't exactly towing the line. And then by the time you get to the 104th Senate, there's only 3 people who occupy that. So the fact that you have the loyalist position has taken over in both sets is a structural equivalence mapping. And that's what this image that Peter showed you yesterday is that we went through and ran Concore on every version of the Senate. And so each of these nodes are structurally equivalent. So this is the loyalist position, but there's individuals who occupy positions that aren't quite the same. And so you can find that sometimes there's multiple, so in this case there's 2 senators, here there's 3 or 4, but by and large, what happens sometimes in the late 90s is the ability to occupy a position within the center of the network that fell out of the grammatical sequence of whatever it is that made being a senator possible in the late 80s, or the late 90s. This is one of my favorite results, is that you said that even the loyal opposition split in this case, right? So it's happened, but that's the beauty of a positional analysis, is that it allows you to see this isn't just a cluster of nodes that happens to vote together, but they also, when they voted together or didn't vote together, they voted differently with others in the network. And so that there was some issue that split them apart. Now the other way of doing this, right? So that was so Concord is the traditional. It's the first thing that people did. It's the thing that got this whole thing started. It turns out that regular equivalence is a slightly different critter, and I like it better, if I'm honest, for at least for many of the kinds of problems that I think that are uniquely role positional kind of models. And so what you're trying to do is you're trying to find nodes that fundamentally just have the same pattern of ties, irrespective of who they're tied to. So it's all about pattern as opposed to about contact. And so in that sense, it's just a pure version of this. And the nice thing we discovered here is that the problem with automorphic and regular equivalence is that they're really hard to calculate the regular equivalent metrics directly. Because what you're doing is you're saying this node, you have its row and column, you have to somehow enumerate the path structure around each node relative to the path structure around every other node in order to figure out how similar they are. And it's just a pain in the ass. And so the classic version of doing this is the Reg algorithm, which recursively defines the degree of equivalence between each pair. So if you imagine intuitively what this does, it says, do we match on degree? Do we match on two-step degree? Do we match on some other function of our step degree? And you keep doing this over and over and over again, and who do I match with? And so it's an iterative algorithm. It's slow. It doesn't always converge. There are a bunch of fine-tuned settings you have to fit, and so it can be relatively fussy. So Ron Burt came up with this idea in 1990, who said, if you and I are the same, then necessarily we should have the same pattern of ties to every other type of third possible tie we could have in the network, right? And so we might be able to exploit the fact that triads already enumerate every possible combination of a person to every other pair of person in the networks and use that as a shortcut to get this. And so that's what he did. And so the way you do this is you take the periodic table of social elements, which is known as this triad census, and you figure out from this whether or not people are in the same spot. And so the beauty of this is that triads are a nice way of locally enumerating social rules. And so if you imagine what a rule that says a friend of a friend is a friend looks like, well, it looks like a friend of a friend is my friend, right? Or a friend of a friend is my friend. And so you can go through each of these triads and say, a friend, well, there's not a friend there, so that doesn't fit. This one is a friend of a friend is empty, that doesn't fit. This is a friend, this doesn't fit, right? So you can identify where does a friend of a friend fit. Or you can figure out where two people that are agree on a third party agree with each other. So this is hierarchical agreement, we have reciprocity. Most of your social processes, if you can state them as a pattern of ties, you can map them back to triads. And so that's the nice feature. And there's good rules for counting on networks where triads exist. And so if I know that every triad in the network looks like this, I know that the structure, the global structure, has to look like this. Just like if I know that every verb in a sentence is in the present tense, then that says something about the kind of document that I'm in, right? So this is the idea. So if I've restricted my sentence structure to being this really simple kind of sentence, you can only have one kind of story. Right? And it turns out that there's lots of difference of these. There's a whole sort of great literature that Eugene Johnson put together on the triadic structures, microstructures leading to necessary macrostructures. I love that work. It's also another set of work that's been abandoned, so if any of you want to take it up, come and talk to me later. But you can then take all of this work at the macro level, which essentially is about the role system, and say which roles do people occupy within that role system. In order to see that, we look inside each of these triads and we identify that there's a slightly different pattern within some and others. And so we can see here, for example, in the 102D triad, you have one reciprocated dyad and the third that they're disconnected from. So these two are equivalent. They're substitutable, you can't tell them apart. And so within this triad, there's two positions. Within this triad, you could be either the end, the bridge, or the starting point, the bridge, or the end. And so there's a different position depending on where you fit in this pattern. And the beauty of this is that this is also pretty simple to enumerate. It's just sorting and counting, like everything else in networks. Once I have that, I can say, of these 36 different triad types, which are the rows in this case, I can ask how often does node A occupy that all empty set, or the dyad position there, or that position there. And you'll notice that there's no identities attached to any of these. It's just which piece of the pattern you belong to. So I can tell you how often you occupy a particular element of the pattern structure. And it turns out that regularly equivalent nodes will have the same pattern. And so what's beautiful about that is that in this case, we can see that nodes A and B have the exact same patterns. Nodes C, D, E, and F have the exact same patterns, and all of these have the exact same patterns. They're not tied to the exact same people, so they're not structurally equivalent, but they're pattern equivalent. And this is a nice way to get that set. Now, we've applied this model in lots of different places, and I have a whole discussion here about how you can go through a sort of example of how we did this in the Prosper data. And I'm just, in the interest of time, I'm not going to go through it completely. But what you do when you do this is you essentially generate this distribution of triads for everybody in your network. And so you'll have a column for each respondent in your network, a row for each one, and then you calculate whatever favorite similarity score it is. And in our case, we just used a hierarchical distance score. I think we ended up using a Euclidean distance, if I remember correctly. And then once you have a Euclidean distance matrix amongst all your sets, you have a hierarchical clustering problem. And so I can go through and say, well, if we cut this network here, this clustering tree at this spot, that gives me some number of positions that all fall under each branch. And those are the positions of my network. So that's the way the process works. It's a classic cluster analysis. Now, we had to do this across 360 or some odd Prosper networks of all the classes and all the waves and all the settings. And so I wasn't going to do that by hand, right? And so what we did is we took this matrix, where'd it go? This similarity matrix, and we said, well, what if we just treated the similarity matrix as if it were a community detection problem, and we calculated modularity on each of the solutions that we could get and picked the highest one, and that's what we're seeing here. So in this particular case, it turns out that 7 clusters is the highest modularity return when we play that little trick. Completely ad hoc. I have no formal theory. Peter hates this solution, but it works, so I don't care. That's fine. So you do it, you get a system that looks something like this. You have a popular core within the school, so these are school networks, and you'll notice that this popular kids, they're popular because every other position sends to them, and they recognize themselves. So that's a classic, this is the way you represent a block model, is the self loops now are meaningful, so the people in the 7 position think that they're the shit, and they nominate themselves. They tolerate another group, the 6, that really like them. So these are the little hangers-on that they're willing to sort of feed a few crumbs to. They think they're cool too, but not as cool as these guys. Then you have an outside clique that is sort of on the bridge set where these guys, they kind of want to be friends with the popular groups who then don't respond back. They recognize each other. But there's this group of outsiders here who are sort of, like, why are you bothering? And so you'll hear the story I'm telling here, right? We have different types of isolated groups. In this case, we have a small group of folks that they actually have some ties in group 2 to each other. They just aren't enough to make it to come across our threshold. And so this is sort of a weakly connected outsider group, and this is a true isolated group, right? And so what's beautiful about this kind of model, and what I hope you picked up in seeing me do this, so this is done on a single relation, so it's not a multi-relational block model, it's a single relational block model. But most of the story comes not just from the fact that 3 is tied to 7 and 6 is tied to 7, but that 7 doesn't tie back to 3. So the zeros, the non-connections from one group to the next, often tell you as much about the setting as the connections do. And that's why it's different from a connectionist standpoint. We're not asking where does something flow through this network. We're asking what does it mean to be the kind of position where everyone wants to be part of you, but you are really stingy with who you're part of. Now, we do this across a bunch of different schools, and so there's a whole story we have in here and how we figure out this for all of these networks simultaneously. But when we do it, we see that across all of these settings, we end up with about 7 different types of clusters across all of these schools. And this is what they look like. So I'm going to skip the details on what they're there. But it ends up being the case that we have a set of really what we call sort of popular loners. So these are folks that others like them, but they never reciprocate. And so these they're high on a hierarchy dimension, they're low on a volume dimension, so they're not engaged in much, and they're, how did I end up over here? Yes, they're low on the volume dimension, and they're low on the reciprocity dimension. So those are the three dimensions. And it's kind of nice that it works out that these things all map up that way, but you end up with these, what the whole reason we started this project in Prosper was that Coleman had this idea that every school had a leading crowd, some set of groups that were really tightly knit to each other, that other people wanted to be part of, and that's what we ended up finding. These positions are unsettled when you're in 6th grade, so when you first start in these schools, all these kids sort of show up into junior high, or into middle school, and you can see that the structure is sort of roughly there, but there's a lot of noise between it, and so people will move from wave 1 to wave 2. You might have started in the leading crowd position. Well, you're likely to end up in one of these others. If you stay in the sort of middle ranks, you kind of move around there, and the loners kind of move around. Every once in a while, you're going to move strong between ranks, but not much. By the time you reach seniors, these things are really pretty well solidified. So your options for changing position over time in high schools, really low. So if you're on the outs, you sort of stay on the outs. If you're on the in, you stay on the in. Now there's a bunch of things that are correlated with this, which I'm going to skip today to talk about, but it's really kind of fun to think about. So I'll go to that later. Now, if you think about it for a minute, this notion of automorphic or regular equivalence, if the defining characteristic is that nodes are indistinguishable on a summary statistic of a network, then why not just cluster summary statistics of a network, right? And it turns out that that's a really fast way to find structurally or regularly equivalent nodes in really big networks, because what you can do is pick, a dozen cheap to calculate summary statistics on the node and then cluster those, and all the nodes have to be the same. And so we've done this on networks of millions of nodes in GitHub in this case, and so you've ended up finding that there are sets of nodes that occupy a lot of different positions that distinguish between sort of members and bridges. All right, so that's the sort of big picture forward way to look at this. Now, I promised to give a little bit of practical advice. If you want to know what I really think, I think that it takes a lot of time to sort of, you should allow yourself the time and energy to go in and do this by hand for a little while and make sure that you understand your setting well enough that you can make sense of the kinds of patterns you find. But once you've done that, then you can jump into one of about 4 different tools. One is the IdeaNet tools. Tom, is Tom here? Tom put together a module in IdeaNet that will do both the clustering version and the Concore version of structural equivalence on multi-relational networks and pick out the best solution by modularity automatically for you. So it's a one button, push it, and get structural equivalence out. And so that's what I really recommend you use. I don't have a slide shot for it yet, but that's we designed it for this exact purpose. And so the whole purpose was that you could take in a multi-relational network, push the block model button, specify a couple options, and get a reasonable solution. And it really does work nicely. Kieran used it in his undergraduate thesis. There's also a great set of tools that Carter Butts put together for calculating regular equivalence and structural equivalence using the standard default metrics from the community. And so if you just use the Sampson data, for example, this is really all it takes to generate a block model, right? So you say that I'm going to take the network, I'm going to get the Hamming distance of similarity for structural equivalence. That's what the SE is. That creates a distance matrix. I can then explore that in some ways, and I can cluster it in the way that you would an equivalence clustering. And there's a handful of options that go with this that are going to bore you today. I dislike the default clustering method. I like Ward's minimum variance. That's just the way that I've played with a lot of these, and I've found that it works the best. And then you can sort of plot what you get. And I'll just show you what the results of this looks like. So when you do this first distance matrix thing, and then ask to plot what it looks like, its default object is a hierarchical clustering tree. So the distance matrix you get out of the structural equivalence says, well, look, nodes 13 and 15 were really similar, nodes 1 and 2 are really similar, and they're pretty distant from node 3. but there are 2 big branches, maybe 3, depending on how you count this split. So I just arbitrarily picked 4 is what I don't know. Yeah, so there's 4 because these 2 are off on their side. So I say cut it here at 4, and that's going to put nodes 1 and 2, these nodes together, these nodes together, and these nodes together. R has some nice heat map functions built in. So again, you can see that 1 and 2 are pretty similar to each other. 12 and 13 are very similar to each other. And these guys are very distant from everyone else. And this is what the network ends up looking like. And so you get one cluster of very popular nodes. They're sized by degree. You get another sort of closed cluster of middling nodes, and then a set of peripheral nodes. Now, you can do this with regular equivalence. And one of the things that I would just point out is that if you look at each of these clusters based on structural equivalence, you'll notice that all the clusters are connected to each other. So this core node is connected to each other, this middling node is, and the 2 different peripheral nodes are all linked to each other. So it's both equivalent and communities. Whereas when you go to regular equivalence, note that this exact same network, note that the hierarchy tree looks very different. It's a much less complex tree, and there really is only 3 different sort of branches here. There's this one way off in the set. Everyone's really equivalent in one position here, and then another set on the side. And what you're getting are effectively a core group of people who have some kind of betweenness ties, so people are nominating them, but they're not nominating others with the same degree. That's the green set. Notice that they're never nominating each other. And the red nodes are peripheral. These 7 nodes are just really nominating others, but notice they're not tied to each other in one block. And so that's the beauty of a regularly equivalent position. This position is capturing people that have the same pattern, even though they're not tied to each other. Now, I don't know if this actually means anything for the Samson monastery data. I haven't put it to a dependent variable, but that's the pattern that comes out of it. And of course, the beauty is you can easily do this with as many different relations as you want. So I can say the business relation and the marriage relation in the Medici data. I'm going to say let's do that as an equivalence class on structural equivalence is the one I used in this case. And I'm going to use the Hamming distance measure. I do it. I looked at the tree and thought, well, there's one group out here that's in one node that's clearly an outlier, and then a couple of others that look different. Let's just go ahead and ask for 4 just to have a look. And when I do that, turns out that the Medici are in a class by themselves, which that's what 6 is, right? And if you read the 100-page long Paget and Ansel paper, you will know why the Medici are by themselves. But that's what you should find. And in this case, you can see that we've plotted this both by marriage and by co-business relations. And you get a pretty canonical set of nodes that are linked just to the Medici or largely dependent on the Medici, and a group that's sort of not dependent on the Medici, which are these guys over here. The other package that you can use is called Concore R. It's a nice package. It works well. It implements the classic Concore methods, and the nice thing about it is this works well with iGraph. So if your favorite R package to use is iGraph, not StatNet, then the Concore package works well. There's another package called Block Model. It does stochastic block models, so don't get confused for what's that doing. It does a really good job of stochastic block models. It's one of the few that does them well. It's really slow, but you get the right answer effectively. All right. So positional approaches, I think, are still underdone, and there are promising ways to do it. The simplest ways to do it is these node clustering methods. I think the thing that I do want to highlight is that unlike community detection, we don't have a lot of implicit knowledge and a bunch of theory built around it yet. It's still a little ad hoc, and it's still a lot of work on the investigator side to do interpretive meaning. I tend to think that's a good thing. I think that this sort of helps us as investigators be creative and to get to know your settings, and it sort of brings a little bit of that digital ethnography sort of flavor back into sociology, so I think it's well worth doing. And once you spend a bit of time, especially with a lot of these collections of networks, like for Prosper or AdHealth or whatever, you can learn what you're doing and then apply it uniformly and systematically across the rest of your set. So that makes it a nice way to do that. And I'll stop there. I've used more time than I was supposed to, and take questions. So thank you. Questions or ideas? Craig, please.
Has anybody validated the 2 different approaches to regular equivalence and seen if they basically yield the same sort of positions?
Not to my knowledge. Someone should. I know that Bert in the original 1990 paper did some very simple versions of that and showed that he could get similar results, and also that he could feed it networks that he knew the structure for and recover those. But I haven't seen a lot other. Please.
What happens when you have, like, what you showed us was a bunch of students who have the same role,
Mm-hmm.
right? And then how they have these other kinds of roles. But what if you have a network where you have multiple roles, like the parent-child network, you know, it gets pretty complicated, right? Like, I guess you could, and theoretically, could you say, would you just sort of see where the parents land in the thing and then?
Exactly. What you would like to do is take a bunch of family networks, and there's actually a data set in the ergom.multi set, which is a bunch of family interaction data. So they have 360 separate families, and they record the amount of time that each family type spent with every other type. So you can know if kids go with parents and such. And if I hadn't been rushing to get the catering done for this gig, I was going to use that as my example to see if my little toy example ever came up, but I never got to it. But what you would hope is that, I drew the picture as the way we might expect it to, sort of intuitively, ideally. But I suspect there's a lot of fathers that look like children, right? That so the mother is feeding them, right? And that they're essentially just a special child, right? And so if that's the case, right, that should pop up. And I think there are many families where the dog looks a lot like the kids relationally. The amount of time you spend with the dog, the amount of care the dog gets, the amount of money you spend on the dog, right? And so there are families in which pets look like children. I mean, the fact that companies have exploited this is exactly why we end up spending so much money on our dogs when my parents never would have done that. But, and so this is so that's a short way of saying yes. What I would do in situations where we have these kinds of formal sort of nominal roles is ask, how often do people actually comport to the role that they're given? How often are nurses actually acting like doctors? How often are patients actually the spouses of patients actually acting like nurses? And so you could figure that out by saying, what kind of interactions are they having with others around them? And it ought to be the case, if you're asking your questions right, and the data set that we have that comes with the software for these families is just time spent. But time spent in a family is a pretty good indicator of what you're doing with them. You don't know if you're fighting with them or you're laughing with them in the data set, but you do know that there are other time use areas where you can get that. But I think those kinds of things, if you collect data about caring and talking and time spent, those kinds of things should give you a lot of information about whether or not doctors, nurses, patients are acting like doctors, nurses, and patients, or whether or not they're taking on somebody else's role. Please.
So I know that you kind of touched on this yesterday, but I'm wondering about whether there are any special considerations that we should take into account for missing data when we're doing this type of model.
No. Right now, all of the models that have been done using this kind of model, for the only information that I know of on missing data and evaluations with this work has been the work that we've done. So I'll have to take that with a big grain of salt because I might not be the best authority. But at least in all the work we've done, your partition of the nodes observed wouldn't differ with and without missing data up until huge levels of missing data. Certainly if the data is missing at random, if the data are missing disproportionately from the central nodes, you will get a slightly different contour position, but it'll still be pretty similar, which is surprising, right? So we did not expect that. We thought it would be more sensitive, but how lucky. Please.
I'm just wondering whether we can talk about the relevance to the research network, because I'm thinking about randomized distribution as a key keyword, primary key keyword in the network, dominating over.
So the question is, what's the relevance to egocentric network analysis? And there are two answers to that question. One is there's a wonderful paper called Local Block Models by Mandel. Mandel and was White on that paper or Borman? Mandel and Borman? I don't remember. It was one of the folks at Harvard. And Mandel was an undergraduate, a math major, when he started this paper. He was working with Borman when he first started, if memory serves right. And so he wrote this one brilliant paper for how to block model ego networks. And then he went and became a banker or something. I mean, we just never heard from him again. And so there's that work out there. And so the local block modeling approach is a formal treatment of this dedicated to local networks. So there is some group on that. The sad part is that paper was written in the 70s, right? And so we haven't done a lot since. That said, if you're collecting ego network data where you collect, oftentimes one of the nice things about ego network data is you typically collect relational enumerators. You're more likely to collect multiple relations on ego networks than you are on global networks because you have them there and it's relatively easy to say, do you do X, Y, Z, and K with this person once they've been named. So you can often get pretty rich multi-relational data on each of those ego networks. And so then what you can do is you can effectively construct a pattern matrix for each of those ego networks and say, does this ego network look like that ego network? And so the ability to do cross-network similarity is pretty straightforward there. Please. Amy.
Oh, yeah. I'm just wondering, so as you were mentioning, a lot of the papers that we're studying in this presentation are several decades old. I'm just wondering what are the contexts in which this kind of additional analysis is most often conducted?
Yeah, so the kind of work where this work has come up, and they're not all been the old papers,
Yeah.
but if you're to contrast, like the age distribution has been like, so it's heavily left skewed. All right. And so the glib answer is that these are University of Chicago Press papers, right? So these are AJS papers, which means something to the sociologists in the room. So these tend to be the kinds of papers that are not hypothesis testing papers. These tend to be papers that are sort of theory generation papers, and they have this flavor of quantitative ethnography, where a lot of historical papers, a lot of work where people are doing interpretive sociology, trying to make sense of a setting, and the relational block model helps them with it. There's two exceptions to that I'm currently aware of anyway. One is a great paper on Brashears, one of the South Carolina guys, that was looking at equivalence and Formula One racing. And what they were doing here is Roger Gould has this wonderful hypothesis that says you don't fight with your unequals, you fight with the people who are like you. You fight with the people who you have some chance when you beat them of establishing a dominance relation, right? So I'm not going to fight with Roger Gould, and he's dead, but he's also so much higher status than me that it would make no sense. Like, why would I pick a fight with somebody who's just going to crush me? It just makes no sense. But, I might fight with Ashton, right? We're close enough in the same level that if I beat him, I'm a winner, right? And so I might actually get something out of it. Whereas, if you're fighting with somebody who's super low, that doesn't make any sense. Like, so me picking on a graduate student is stupid. Why would I do that? Right? That would just bring me down. So Gould's argument is that conflict happens among status of equals. And so what this paper showed really, really brilliantly is that if you look at races, it's the people who are in equivalent position in the racing rank that will bump into each other on the racetrack and sort of exert their dominance over them in a way to try to get ahead. And so that's some really good work. And the other work is Ivan Chase's work on equivalence relations and dominance hierarchies for all kinds of critters, which he's done now. And so his goal is to try to figure out what makes a hierarchy. And so in order to get that, he's been using some of these methods. All right, I now have taken too much of Ashton's time, so I'm going to stop there. And thank you, folks. Again, I hope you use this work, and we'll see you.